Okay, so I wanted to finish off this mini tutorial series by talking about the third option that I frequently use for analyzing data, which is the programming language Python. And so I kind of am going through these in order of sort of increasing overhead and to some extent learning curve, because there's things like Excel and Google Sheets and LibreOffice Calc, spreadsheet programs where you can just kind of open them up and do things very easily, but they're fairly limited. There's Octave, or equivalently MATLAB, which is kind of in the middle and is what I would probably most strongly recommend, where you interact with it by entering these commands, and it acts more like a programming language, but it's still fundamentally kind of optimized for data analysis and number crunching and not that good for general purpose programming. And then there's Python, which is more of a general purpose programming language, although it skews more towards these sort of data analysis tasks. And so there's kind of the most overhead to learn how to do anything in Python. But it does offer some additional flexibility that can be worth it. So we're going to go ahead and run this little Python script here, which I've pre-written because you can run Octave via pre-writing a script like this. So I'll run this Octave script and it'll generate this nice figure for us. Or I can run this Python script and it will also generate this nice figure for us. Although again, of the three, I would most strongly recommend Octave / MATLAB for data analysis, but there's no harm in learning all three. So, like I said, Python, you can use it just by entering one command at a time, and you can open up a number of different ways to do this. So this is the idle, the development environment that comes with Python when you download it. You can just do 1 + 1 and it prints out 2, or you can use it like this. And you can also use a different development environment if you want. It being a general programming language, you can use Visual Studio, you can use Emacs, you can use whatever you want. But I recommend, especially if you're a beginner, just using this idle environment. So let's pretend I didn't have this script already written. So let's just do File, New File, and we're going to start writing something from scratch, although it's just going to be a copy of that script. So unlike Octave, you can't just automatically start importing data, right? Because Octave, we just go, CSV read. But in Python, we have to import the libraries that we want to use with this import command. So we're going to say import CSV, which is a library for dealing with comma-separated values. Because remember, like in the Octave tutorial, we start with this data that is written down by hand into a spreadsheet program, and then export it as what's called a CSV file. And so CSV, let me just show you, is a very simple format where if you open it up in a spreadsheet program, it looks like this, where data is in a table. But if you open it up, you can also just open it up in a text editor. Let me open it with a nice WordPad. See, it's just lists of numbers separated by commas, and then each new row separated by just a row. So I know let's not save. And so that's a very simple but versatile format. And we're going to read it into this Python script. So we're going to import CSV. And first thing we're going to do is, unlike Octave, we kind of have to initialize our variables a little bit more. Python is pretty flexible because Python and Octave are both, it's called interpreters or scripted languages, so you don't have to do too much programming, but let's just still open these arrays, and we're going to call them X, T, and S, so we're just creating these, arrays or lists of numbers, and we're initializing them as just empty, which is what those brackets do. And so this is where we have to do a bunch of commands that get kind of complicated, and I recommend just copying and pasting all of this code. So we're going to say with open speed.csv, which is the name of the file, and then new lines equal to empty, because it's nothing, as CSV file. And then in Python we have to do a colon before we go inside of a loop like this. And then we say data reader equal to CSV reader of CSV file, comma, delimiter equal to space, comma, quotechar equal to vertical bar, close parentheses. So that'll create our data reader. And then we're going to say for row in data reader, again, colon, and then we're going to go inside of that loop. Say, first thing we're going to do, just to make sure everything works, we're going to tell it to print quote, comma, end quote, dot join row. So there's kind of a lot there. It's what you did when you just basically Google how to read a CSV file into Python. So I recommend just copying and pasting this code. Either you can Google it for yourself and play around with it, or I'll just make the Python file available. In fact, it's short enough, I'll just put the whole file in the video description. But so let's go ahead and press F5 to run this, or we could go up here and go run module. So first we're going to have to save though. So let's call this analyze Python, and let's save it in the correct directory here. Save, and oh, new lines. All right, so let's see, where did I make a typo? Oh, it should be new line instead of new lines. And where else did I make a typo? Oh, right, csv.csv reader. Remember, in Python, everything comes from these modules that we import rather than just being part of the scripting language by default. Oh, csv.reader. There we go. Oh, quotechar, not quotechat. There we go. And there's our list of numbers. So that seems like, if that seems like kind of a lot of work just to get to the point where we have our data listed for us, you're right. Like I said, it's a little bit higher overhead, but Python does come with some additional flexibility. This is why I recommend, out of the three options, Octave/MATLAB the most, but we're going to do Python because some people prefer Python, and it does offer some extra libraries that aren't necessarily available in Octave. Okay, so next thing we're going to do is we're going to put this data into these arrays we initialized up here so that we can start analyzing it. So we'll do t.append, and we have to convert everything to a floating point number, and then row 0.split and so we're splitting it on the commas, which, because that's CSV stands for comma separated value, and then index of 0. And let's make sure that that's correct. And then we can go back over here and check. If we just enter T, press T, enter, and there's our list of times. Okay, so now let's copy and paste that. But we'll do x.append 1, and finally s.append 2, because the second and third columns in each row correspond to distance and speedometer readings. Okay, so now we finally have our data in a usable form loaded into memory in our program. So t X, and S are all now available. So now I'm going to correct something that I actually made a bit of a mistake in the Octave video, which is I forgot to save the time in seconds. So we're going to save our time in seconds as TS for time seconds equal to T. And then we're going to set T equal to T divided by 3000 divided by 60 divided by 60, so that we now have time measured in hours so that we can compare miles per hour to miles per hour. And then let's just go ahead and print T, print X, print S to do what I just did there so that we can make sure we're getting what we want. Oop. All right, so this is where we need to start doing something a bit different, where another downside of Python, although it's not a huge downside, is again, in Octave, if we want to divide an array by a number, we just press divide. In Python, it's not so easy, so we're going to have to import a library called numpy, which you also are going to have to install. So say import numpy as np, which the import command imports a library, and as just changes the name of that library, so we don't have to type numpy out every time we want to use it. So if we want to just divide an array by a number, we actually have to do np.divide t, 60 times 60, and press run. And then now we get what we wanted. Okay, so now we have times in hours and times in seconds available to us, and we have the numpy library available to us. And so next we're going to need to import something called matplotlib, which matplotlib is what it's going to let us create plots. And we're going to import matplotlib.pyplot because that's the easiest part of it to use. We're going to import that as plt. And now let's come down here and let's say, first of all, let's make sure to close all previous windows just in case something gets left open, some previous run of the program. And well, let's do a plot just like we did in Octave. So we'll do plt.plot, time in seconds, X, and just like in Octave, we can choose different line styles. So we'll say blue diamonds, B, D, and then dash, so we have a line connecting them. And then F5. Oh, forgot to close quotation mark. And, oh, nothing happens, does it? So unlike in Octave, it doesn't just automatically show up. So we're going to have to do plt.show and then run the program again. And now it'll show up. And so there's our position data point, or those are our position data points as a function of the time in seconds. Let's close that. Okay. So now let's say we want to do a fit just like we did in the previous example in Octave. So we'll do plt, or sorry, not plt. We're going to use the numpy library to create a fit. We're going to do the fit, we'll just call it that. It's equal to numpy.polyfit, which is just like the polyfit function in Octave/MATLAB. And we're going to feed it those numbers, and it'll spit out a result for us. The F5. And now let's see what the fit. Oh, stuck on that figure. So now let's see what values we get for the fit, and it's actually, all right, so there's our 3.57 times 10 to the 1, so 35.7 miles an hour, 36 miles an hour, just like we got in Octave. All right, cool, cool, cool. So now let's try plotting that on our graph. So we will do plt.plot, and we'll do time in seconds, comma, oh, actually, numpy.multiply time, comma, fit sub 0 plus fit sub 1. And let's make that red. And hopefully I did that so that the scaling will all work out. So we'll find out in a second when I fix these close parentheses issues. One too many right there. Yes. So now we have exactly what we wanted. This red line that represents the straight line fitting these data points as best we can, and the actual data points themselves, all in one graph. Okay, so now let's do subplots, just like we did in Octave, where we want to have two graphs on the same figure. And we always have to put plt.show at the end. And so let's see. All right, so now let's do plt.subplot 2, 1, 1. And let's make sure that gives us what we want. Yep. All right. And so then plt.subplot 2, 1, 1, 2. And then plt.plot ts, s, speed. And then what type did we want for that? Green circles. Okay. GO dash will give us green circles with a connecting line. All right, there we go. And now we want to calculate the piecewise average velocity and also plot that on there. So we're going to need to use numpy again for that. So we'll do speed is equal to numpy np.divide numpy.difference of x, numpy.difference of t, and close parentheses, and plt.plot time in seconds, speed, red diamonds, because that's the convention we decided on for last time. And there we go. Oh. Oops. Speed. Because there's S for speedometer and speed for average speed. Oh. Oh, right. But we have this problem of they're not the same lengths, right? Because when we take the differences, you need at least 2 points to take a difference. And so we have an array that's one shorter. So to fix that, I do time in seconds, index 1 colon. In Octave, it's 1 colon and. In Python, it's just 1 colon or index colon will go to the end of the array. All right, there we go. But see, now they're offset, so we need to fix that just like before. So to fix that, we're going to do minus numpy.average of numpy.difference of time in seconds divided by 2. And that will offset all the data points. Did I misspell? Oh, no. I keep saying the actual words. It's np.diff, right? So I'm saying the English language word for what I'm doing, but of course when you're typing it's much better to have the shortened version. Okay, so now we have the graphs that we had before where the position is plotted as a function of time, and we have this red straight line fit to it showing an approximately constant speed, and then also have this line showing the piecewise velocity in each of these segments shown in red, along with the speedometer readings shown in green, and showing how those roughly align with each other. And so finally, let's just add a little bit of formatting like we did with Octave. So let's say we'll do plt.xlabel time s for seconds, and plt.ylabel distance miles. And likewise, let's go down here and do plt.xlabel. Actually, why do work we don't have to? Let's just copy and paste, because xlabel is the same, and then ylabel speed mph miles per hour, and let's do that. All right, so now we have our graph just like before, and you can also save it if you'd like. Just call it figure 1, and there you have it. So that's how to do things in Python. Like I said, it's a little bit more overhead than in Octave, but you can produce these same graphs that let you understand what's going on. I am not going to necessarily assume you know how to use any of these programs for the actual rest of the lecture series. I'll just be showing these plots, and I think it would be tremendously beneficial for anybody who happens to watch them to learn how to do this. So if I ever get around to actually teaching students in a real class, which is my fundamental end goal, I'd like to make it clear how to use all of these programs, because they're very, very useful. So yeah, hopefully that was helpful. Bye.